Good morning, everyone. Today we will look at rectifier circuits, finish up rectifier circuits with the equations, and then get into Zener diodes. Okay. So we begin first with the half-wave rectifier. Now, those of you who completed the lab yesterday, this will look familiar. So we analyzed all of the rectifier circuits using the ideal diode model. There was no voltage drop, right? But if you want a more accurate values, then we actually plug in the either use the constant voltage drop model, or we can use the actual voltage drop as specified in the manufacturer's spec sheet. So here we are using the constant voltage drop model, meaning a certain voltage is required to turn the diode on, right? So this is the CVD model, constant voltage drop model. And for the purposes of our course and our book, we take this approximately equal to 0.6 volts. Obviously, that depends on the kind of diode that you're using. And so 0.6 volts is required to turn on the diode. Okay, turn on the diode. And so a little bit of the input is used up to turn it on, as you can see in the illustrated graph. And so the output voltage is VP minus whatever that turn on voltage is. So output voltage V out, or in this case, since we are saying we have DC at the output, we can write it as DC. VDC is VP minus V on. Now at this point, actually I should, let's cover a little bit of the basics of sine waves. Taking you back to 211 and 212. Time on the x-axis. This is mathematically represented as V of t is Vp sine omega t plus or minus theta. We keep the angle in degrees separate from the omega because we want to use phasor transformation. And for phasor transformation, we need magnitude and the phase angle. Now, the time varying waveform can be represented as a vector that is rotating inside a circle. I should have drawn the circle first. Okay. That's 0. This is 0 degrees. This is 360. Right? It rotates in the counterclockwise direction. We can write the phasor or this voltage as VP with a phase angle of theta. Look familiar? Right? Hopefully it rings some bells. This is 360 or 2 pi. And this is pi or 180 degrees. Pi by 2, 90 degrees. And this is, of course, 0. And then this is one full time period t. Right? This is what we are applying as input to our rectifier sine wave. Okay. F is the reciprocal of the time period. Okay. Familiar, right? Okay. So now when we apply our sine wave, we just saw that a little bit of the voltage is required to turn the diodes on. And of course, this is not quite a full flat line, right? I like to personally call it as both AC as well as DC, because the value of the waveform is constantly changing with respect to time. So the output waveform even though we refer it to as DC, the output waveform still has values that fluctuate with respect to time, right? I personally like to call it as AC as well as DC. A technical term would be many different authors and different people use different terms. Our book uses pulsating DC, which I'm fine with. Pulsating DC. Anyway, the point is that this is not quite what we would require to run our devices, right? So we add on a capacitor, or we use the energy transfer phase of the capacitor to smooth out the waveform into a near flat line. And so we connect a capacitor at the output, meaning across the load resistor R. Okay, across the load resistor R. And when we do that, we obtain a waveform that looks like this. Now, this is, of course, exaggerated. An actual DC waveform from the capacitor would not look completely flat like this. This is for an ideal and large capacitor. Okay, so we add a capacitor at the output. And what that does is T and V out or VDC. What the capacitor does it smooths it out by using the energy storage and energy transfer phase of its analysis. So if we have the output of a half-wave rectifier that looks like this, and we connect a capacitor at the output, current, when it comes from the transformer from the diode, positive half cycle, diode is forward bias, current flows to the capacitor, it charges up, plus at the top, minus at the bottom, current's coming from the top. So capacitor charges up. Now it charges up, diode is almost like a short circuit for the capacitor, except for the small forward series resistance of the diode. So when the positive half cycle, the circuit is actually like this. You have a battery, you have a diode, forward diode resistance, and you have the capacitor. And that's the direction of the current flow in the circuit. So capacitor charges. Tau, in this case, would be actually not FR, RF, forward diode resistance, RF. Tau would be R times C, and that would be the forward resistance times the value of the capacitor. Since that series resistance is very small compared to the rest of the circuit, total tau is also small. And the capacitor is able to reach full charge at the top of the peak right here. So VC is at full charge. Yes.
Is that forward resistance representing the diode when it's on?
Yes, that is correct. Forward resistance is when the diode is on. Okay. Right. So the time constant is small, capacitor charges, reaches full charge. And obviously there's a fine line between choosing the capacitor value large enough so that it provides us a near flat line at the output versus trying to make it small enough so that it is able to reach full charge. Okay. If the capacitor is too large, it probably may not reach full charge in the first cycle. It might take a few cycles for it to reach steady state. So far, so good. Right. And then negative half cycle. Polarity is reversed. The half-wave rectifier diode is represented with an open circuit, or in real life, you would have the reverse resistance, very high reverse resistance, almost close to infinite. Okay. And now the capacitor begins a slow discharge. Okay. It begins a slow discharge. Now, of course, it'll try to discharge through the diode. So the diode is reverse bias, not going to be able to. And so the output of the capacitor is a nearly flat line. Okay. So if we go back to the top, this time, sorry, not V out. Tau would be reverse resistance times the capacitor value. Very large. Hence, a very slow discharge. If this was an ideal circuit, capacitor wouldn't discharge at all. It would just stay flat. That is what is represented here. Ideal capacitor. Ideal capacitors can hold their charge indefinitely. Right? The real life capacitor starts discharging. At some point in the future, capacitor VC, voltage VC for the capacitor would reach 0 volts. But before it can reach 0 volts, it gets interrupted with the next positive half cycle and starts turning on again. Yes. Oh, because it's a negative half cycle. So that is one way of representing the negative half cycle. So if you're just illustrating, so the question being asked is, why have we flipped the polarity of the voltage source? It is to represent the negative half cycle because the voltage is now flowing in the opposite direction. So where was I? Oh, yeah, here. So positive half cycle, the second one hits and the capacitor starts charging again. So the overall output is now here, right? If we think of them as, well, mathematically area under the curve, right, which would be this. And find the average value. That average value is basically our actual DC voltage. So for example, if you were to take a multimeter in the lab and measure the DC output voltage, it would turn out to be about 0.318 times VP. So the average value would be somewhere here. And that average value .318 times VP. Okay. So far, so good. Now, the diode is actually not on all the time. It's only on for a certain portion of the time, right? For the rest of the time here, for the output at least, if you take this portion, this energy is coming from the capacitor. So it's not coming from the input. That is stored energy that is coming from the capacitor. So now your capacitor has raised, now if you take the area under the curve, your capacitor has raised the level of the DC voltage. Does that make sense to everyone? Right? And so thus it has removed the AC component, or not the AC AC voltage, not removed, but it has smoothed out the AC voltage to as flat as possible, meaning a DC line. Yes. Question? Okay. And what is left behind, there are two questions to go. I will get to that a little bit. Yes. Yes. So the point being made was, if we, well, mess the capacitor value, but basically if we calculate the capacitor value such that we can try to get as much of a flat line as possible. But the earlier statement I made was there's a fine line between trying to get the capacitor value as large as possible versus having it small enough so that it reaches full charge. Because if it is too large, then the time constant during charging is also large, and it may never end up reaching a full charge, which is a possibility. So there is a fine line between trying to get it large versus keeping it small enough so that it reaches full charge. But again, this has been in existence for decades. So, at its most basic, we can take a small transformer, connect a single diode, connect 1,000 microfarad capacitor on it, and you get a reasonably flat line. Yes.
Why do you say like one cycle?
1/60th of a second. That is correct. Yes. You can. The point being made is about why can't we have a capacitor that is larger than the 5 times tau? That's possible. Even if it doesn't reach full charge in the first cycle, it may reach charge in the second, third, fourth, fifth cycle. So it would reach full charge eventually. Yeah. All right. Did you have a question? Okay. So once it reaches full charge, it's discharging. The energy from the stored energy in the capacitor is now being sent to the output. The diode actually is not on all the time. It's only on for a small period of the time. And that is this period right here. Okay. Because here's what you need to think about. Capacitor is plus, right? It's already charged, right? So even when the next positive half cycle arrives, which is at this point in time, right? This is when the second cycle begins. Second cycle begins right there. Even at that point, the capacitor is holding the cathode of the diode at a higher level, which is like right here. The cathode of the diode is not at 0 volts. Right? Does everyone see that? The cathode of the diode is held at a higher potential because capacitor is supplying that energy. So the diode is not on, not yet. It turns on when the V in exceeds, meaning the voltage at the anode exceeds the stored energy of the capacitor. The diode turns on at this point right here. And this is noted by a term called delta T. Delta T. So diode is only on for that portion of the time. Once it starts dropping, diode turns off, capacitor starts discharging. So the diode is only on for that portion of the time, which is known as delta T. This is known as the conduction time, and the corresponding angular value is known as the conduction angle. Actually, let me write it here. So the diode conduction time is represented as delta T, and the corresponding angular version is the conduction angle. Conduction angle, that is theta C. Okay, delta T and theta C, where T is in seconds and theta is in degrees. Or if you wish to do angular, then radians per second. Radians, sorry. Okay, 10-second pause. Questions? Yes. Zener diode after this? We can use a Zener. Zener would work the same as any regular diode in forward bias, but it will also conduct in the reverse bias. It's just not what we want. So, if it's simple forward bias application and the reverse voltage is going to be less than the Zener voltage, then you could potentially use a Zener diode, because a Zener diode will work as a regular diode in bias. Depends. No, we can get Zener diodes made from like 2-3 volts going all the way to like hundreds of volts. The transformer, no, the transformer is just 2 coils. It doesn't have anything else in there. Yeah, no. Okay, so the next point is, what about this leftover AC? Right? In real life, you can never have an absolutely smooth line just by a capacitor. Capacitor, overall DC power supply, capacitor is just one component, right? It's filtering out and smoothing out the pulsating DC into a almost flat line, but it's almost flat. It's not completely flat. So the last remaining vestige of this AC voltage looks like the surface of an ocean, right? Ocean, if you look from very far off, it's almost flat, but it has ripples of waves. And that's what this looks like, hence the name ripple. And because it is representing the AC voltage, it is known as the AC ripple. Okay, an AC ripple can be measured in both peak to peak as well as RMS. And the actual DC value would be a combination of this DC value plus the AC RMS value of the AC ripple. Now, if you're just using the capacitor, then that ripple, let's say, typically would be about 100 millivolts or less. So if you have a DC power supply that's about 10, 12 volts, that ripple would be like, less than 0.01. Okay. All right, let's take a pause. Let me know if you have any questions. Okay. So we can technically define or mathematically define the ripple voltage, represent it as VR. And VR can be given by the V out, which is the input voltage, 1 peak, minus the diode turn on voltage, times the time period, T, divided by the time constant, RC. Okay. So the output voltage, Vp, minus the diode turn on voltage, V on, times the time period, one time period, divided by the time constant, R times C. So that begs the question, where did the R come from? And that's part of the design consideration. If you're working with DC power supplies or you're designing a DC power supplies, we have to design it to work with a wide variety of loads, going from like 10 ohms, 15 ohms, all the way to hundreds of kilo ohms, perhaps. Okay, so that is part of the design problem. So this R right here signifies the load resistor. As an engineer, if you're designing a power supply, you are designing it to work with a large range of resistor values. Okay, so cheaply designed power supplies but sometimes may or may not work with everything. For example, if you're buying a specific device, and this used to be very common with like cordless phones, and if your kids ever use cordless phones, cordless. What I would say wireless phones, but wireless phones mean something else now. Cordless, C-O-R-D, cords, less phones. Have you ever seen those? Used those? Yeah, hopefully sometime. All of those used to be sold as like a set where you have a base station, you have 4, 5, 6, one handset to put in every room of your residence, or if you're in an office, you could put one in every cubicle. Okay. And so all of those used to come with like these small DC adapters that you plug into the wall. Remember I said I used the term called wall warts. So it used to be all power outlets would have like this kind of adapter, and people did like look at those. So they came up with a term called wall wart. And each one of those had a transformer. Each wall wart was a power supply transformer, and was designed, that DC power supply was designed to work with only that cordless phones, right? So they already knew what kind of load resistance they were facing. So if you could try and use those with something else, it may or may not work as good as it's supposed to do with that device. Which is also one of the reasons why manufacturers state that, you know, only use the rated power supply that comes with the device. Nowadays, it's not so much of an issue, but manufacturers still like to state that. Now you can simply plug and play and switch it out because everything is standard spec. But anyway, coming back to our equation, that R signifies load resistor. Okay. And then we can also define, we can rearrange the term, and we can define that the current flowing through the circuit would simply be the voltage divided by the load resistance, R. And then VR can be reduced to IDC times T over C. And then we can rearrange the terms, and we can also write a capacitor value can be designed in terms of the desired current and the desired ripple voltage. So you choose the capacitor, choose the diode current for the application, sorry, the current for the application, and then you can calculate how much your ripple voltage would be. Or if you want your ripple voltage to be a certain level, you can calculate your capacitor from that value. Make sense? All right, 10-second pause. Let me know if you have any questions. There's a couple more equations after this. Yeah, about 16. There's 23 students at 8 o'clock in the morning. I'm surprised. Okay. All right. So we were talking about conduction angle. So that can be given by this equation, the root of 2VR over VP, and then delta T, of course, can be written as the conduction angle over omega, 2 pi F. And then the last specification is the peak inverse voltage or the peak reverse voltage. And that is the spec of the diode. Basically, how much voltage can the diode handle in reverse bias without breaking down, without entering the breakdown region? And it must be at least twice the peak value of the voltage. Okay, 2 times peak. So it must be approximately 2 times the peak value. Okay, so these are the terms in the equations of the half-wave rectifier. Good. Question? Okay. Now just waiting for students to finish writing it down. Now, the filter capacitor, we apply to half-wave rectifier, applies the same way to center tap, applies the same way to full wave rectifier. We have a rectifier circuit, irrespective of whether it's half wave or full wave, we do have peaks, right? It's pulsating DC, or as I like to say, AC/DC. And so we have both AC as well as a pseudo DC in there. So we apply a capacitor, but for a full wave rectifier, now we have 2 peaks. So twice as much frequency. So if it's a 60 hertz signal input, half wave will still have 60 hertz at the output, but a full wave will be twice as much, so 120 hertz. So most of the equations are still the same, except there are some places where we double everything. The first place where we double it would be the diode turn-on voltage. So for a bridge rectifier, I'll come back to center tap. For a bridge rectifier, there are 2 diodes for every cycle, for every half cycle. So the diode turn-on voltage is double, right? So if you use the constant voltage drop model, then it requires 2 diode voltage drops for every half cycle. So V out or VDC would be peak minus 2 times V on. So that is a downside, but that's easily fixed by just increasing the input. Okay, we just have a transformer that gives us a slightly bigger output. Okay. Correspondingly, IDC, of course, is also VP minus 2V on divided by R. Okay. The other equations remain the same. VR is still VP minus V on, but in this case, of course, it's 2V on over R times time period over 2C. Everything is doubled. And so now time constant also is double T over 2 times RC. And then delta T is still the same, conduction angle or omega. And theta C is root of 2VR over VP. And because it's 2 diodes in series for each half cycle, the peak inverse voltage that every diode must handle is cut in half. So instead of being 2 times VP, this is just VP. So peak inverse voltage or peak reverse voltage is equal to VP, which in real life is not a problem at all. The 1N4000 series goes all the way from like 50 volts to 1000 volts. So you could stick a diode in the wall and it'd be just fine. Not all of them, but think 50, 100, 200. So I think 1N4003 to 1N4007. That's what's in our chargers, actually. All the mobile chargers that we have nowadays. The reason they are so lightweight is because you first take the 120 volt input and you directly rectify it into DC. So it's high voltage DC in a way. And then we convert that DC, we step it down, and then we convert it back to AC. And so when we convert it back to AC at a lower voltage, the size of the transformer is very small. And it's very high frequency. So you convert it to high frequency AC. Size of the transformer is small and it's lightweight. The transformers that we used in the lab yesterday, heavy. That's how all of them used to be. One of the advantages over those kind of transformers is that those transformers are fixed, meaning the input voltage to those transformers, and I'm going on a little bit of a tangent. So the transformers, you can only give 110, 120 volts input. So you can't use it anywhere else outside of North America. But all the mobile devices, mobile chargers, doesn't matter what the input is, going all the way from 100 to 240 volts AC, the diodes can handle that high value of an AC signal. You simply rectifies it directly into DC, then it's stepped down, or not stepped down, it's converted to a lower voltage after rectification. And so all chargers that we use nowadays can be used anywhere in the world. You don't need an electrical conversion. You only need a physical conversion. Yes. Yeah, you had a question. I saw a hand that was raised. Okay, second time. Yes. There's a circuit. Well, there's a device called inverter. Inverter. We don't study it in this class, but I'd be happy to discuss it outside of class. Yes.
You said the devices will work in other countries for their different voltage levels, but what about for the different like frequencies?
It can handle, yeah, it can handle 50 to 60 hertz easily, just fine. Yeah, because again, if you look at the rectifier circuits, if the frequency is 50 hertz, 60 hertz, 100 hertz, 1000 hertz, doesn't really matter. As long as the diode can switch fast enough, and these regular rectifier diodes can switch fast enough. So 50 to 60 hertz is not a problem. It's a good question. Question being asked is, if you're taking our chargers worldwide, can they handle 50 hertz frequency? The answer is yes. They can handle 60 hertz here, so they can handle 50 hertz outside. In the lab, for those of you who did the lab yesterday, we were applying 100 hertz. We could also apply 1 kilohertz, and it will still work fine. So let's see. Peak inverse was P. Center tap works the same way. You add a capacitor at the output, 2 peaks, but it requires only 2 diodes. So each half cycle, again, a diode, only one diode, not two diodes. So the VDC or V out is still VP minus V on. Only one diode drop voltage. Okay, only one diode drop voltage. And VR, the ripple voltage, is the same, VP minus V on over R times T over 2C. Delta T is 2VR over VP divided by omega. So it's 1 over omega. That's the same equation, no difference. Same equation. Okay. So if we wish to compare and summarize, we can find the capacitor value depending on what kind of ripple voltage we desire. Now, obviously, as I stated, in real life, an entire DC power supply is much more complicated. We have a lot more components in there. One of them being a Zener diode. The Zener diode can hold the voltage constant when it's working in reverse bias. And so Zener diode is a very popular voltage regulator. You simply connect a Zener diode at the output, and the capacitor, which has, which capacitor output, which might have some ripples, would be eliminated. All we have to ensure is that the input voltage is large enough to actually turn the Zener diode on. And that we'll study right after this one. Let's see. So center tap, bridge rectifier. Oh, any questions before? Okay. So here's a little bit of a comparison between the three rectifier circuits. We already studied this, we already looked at these equations, right? We can figure out the capacitor value based on the desired ripple. And then simply rearrange the terms. The peak inverse voltage for a full wave bridge is reduced in half, or it's cut in half, because there are two diodes to handle each one of those. When you connect diodes in series, you're adding on how many, you're adding on the peak reverse voltage, right? Because it drops equally across each one of those diodes. Let's see. All right, Zener diode. Yeah, just enough time maybe to perform one single load line analysis. So important thing to keep in mind is first that Zener diodes always work in reverse bias, or always used in reverse bias. Using them in forward bias is just wasting money in that sense, unless that is the only option we have available. So always works in reverse bias. So reverse breakdown. Also, important thing to keep in mind is earlier in this chapter we referred to it. When diodes work in reverse bias, there are two breakdown mechanisms. One is the Zener effect, the other one is the avalanche effect. But for all intents and purposes, if we are using a breakdown diode, doesn't matter what the effect is, they're all referred to as Zener effect, which is technically, it would be incorrect, but that is just become the de facto norm. Okay, so use a diode in the reverse region, the breakdown region, all referred to as Zener diode, Zener effect. So in the reverse bias, this would be minus VD, and this would be minus ID. And I'm exaggerating the characteristic right now. Okay, this is way too exaggerated. This is like in nanoamps at worst to like a picoamp range. Very, very small. So small that you can't even measure it. Okay. We recall lab 1, where we simulated, sorry, not lab 2, where we simulated reverse bias in PSpice or in SPICE program. We had to zoom into the picoamp range to actually see a reverse bias characteristic. Also, when we did diode characteristic last week, using sweep and go in the reverse bias, again, we had to zoom into the nanoamps range to actually see this kind of curve. So for all intents and purposes, it's a flat line at 0. So it's a flat line on the y-axis, or the negative y-axis. And then it reaches the breakdown, which would be somewhere here, depending on the design of the Zener. Right here. And from that point on, it's a near flat line. So once it reaches the breakdown, it's a near flat line. It's the breakdown voltage known as the Zener voltage. And diodes are specifically fabricated or manufactured with heavy doping. So the fabrication process requires heavy doping, meaning a whole bunch of dopants in a very small area, so that when it's reverse bias, it can quickly enter its breakdown region. Yes. No, that's correct. It's negative voltage and negative. Oh, yeah. I just got what you're saying. Thank you. Yeah. So only one student is paying attention. Everyone else needs coffee. Thank you. Yeah, minus VD. Voltage is always on the x-axis. Current is always on the y-axis. So VZ is where the diode breaks down. But the main point is that once it breaks down, it keeps the voltage at a near constant level. So Zener diodes are always used in reverse bias. So the cathode is always connected to the positive end of the supply. So in this case, we are applying a voltage. Now, we are simply applying a DC voltage. Okay, we are not talking about like AC or fluctuating or pulsating DC or anything. It's a flat line. It's a flat DC voltage that is being applied. In this case, it's a 20-volt input supply, and the Zener diode is designed to break down at 5 volts. So the way we analyze, when you look at a circuit, the first thing you must understand is that the output of the Zener would stay at VZ. So V out will always equal VZ as long as the input is higher than VZ. Okay. If V in is greater than VZ. If V in is less than VZ, the diode is not going to turn on. So if V in was 4 volts, if V in is less than VZ, diode is off. If V in was 4 volts, diode is not going to turn on. You'll only get 4 volts at the output. Okay. The Zener diode is going to be off. So the resistance is going to be high. Excuse me. And so the output is simply be the input. That's all. It's not going to turn on. I stated too early that we'll do the load light today. Let's see what else. Zener diodes, 2 ratings, actually 3 ratings. We have the Zener diode voltage, VZ, Zener resistance, and then we have the power dissipation for the Zener diode. All 3 of these are important values, and we will look at those, I would say, next class on Friday. Okay, just in time for lab next week. Okay. Huh? Inverters, yes. DC to AC inverts it. Well, there's a whole circuit and explanation behind it. Oh, before I forget, Friday I have an appointment, so I won't have office hours. I can meet for maybe 10 minutes after 10 o'clock, maybe 10, 15 minutes. But then I have to be off campus, and then I come back. I have a 4-hour seminar meeting that I'm attending. And so I won't be available on Friday. Okay, but I will be available today as well as tomorrow. Yes. Yes, I'm gonna set one this week. Maybe due directly on Sunday. So I'm gonna, yeah.